Good morning. I am Ashwini Kumar, today's host. Welcome everyone with great pleasure and enthusiasm. We, the SEST, the official Civil Engineering Student Technical Club of NIT Rourkela, we continuously provide a platform where you can interact theoretical knowledge with practicality. Our club has continued its legacy since 2012. Let's have a glance at our club through a short video. Introducing executive body of SEST, whose continuous effort make the club great success. Mr. Biswaprakash Bahinipati, the Vice President of the club, and Miss Mehak Fatima, the Secretary of the club. We are on board to introduce CIVI-NAR, an exciting combination of connectivity and knowledge. This platform allows us to explore the most innovative subject of present and the future under the guidance of experts. So today's conversation explores the fascinating subject of research and development in ocean engineering. Going forward, we are graced by the presence of Professor Ramakrishnan Balaji on board. His expertise leaving an incredible mark in ocean engineering, coastal engineering, and nearshore dynamics. Professor Ramakrishnan Balaji did his master's and PhD in ocean engineering from IIT Madras and currently serves as an associate professor in Department of Civil Engineering at IIT Bombay. Now I invite the Vice President of the SEST Club for his warm greetings.
Good morning, everyone. This is Bishwa Prakash, the Vice President of CES Club. It is with great pleasure and immense enthusiasm that I extend a warm welcome to all of you to the seminar series organized by the CES Club of NIT Rourkela. Today, we are honored to have Professor Balaji with us as a distinguished guest lecturer, and we are thrilled uh, to have all of the CES members on board for this event. The seminar series is a platform where knowledge, expertise, and ideas converge, and we are delighted to see such a wonderful turnout. Your presence here today reflects your dedication to learning and your eagerness to engage in meaningful discussions. Professor Balaji, we are truly privileged to have you share your wealth of knowledge and experience with us. Your insights are sure to inspire and enlighten us, and we eagerly anticipate your lecture. To our esteemed audience, thank you for joining us. Your active participation and curiosity drive the success of the seminar event, and we look forward to your valuable contributions during the discussion. Let us make the most of this gathering and embrace the opportunity to learn from one another. Once again, a warm welcome to all of you. Thank you for joining us.
Now I kindly request that Professor Ramakrishnan Balaji to continue with the presentation.
Okay, good morning to all of you. Before I start the presentation, Ashwini and Bishwa Prakash, how much time I have got to make the presentation?
Sir, probably like approximately 30 minutes or something. Sir, it's totally upon you. You can go on with the lecture as long as you can.
Mess up your schedule. In case if you have a specific schedule, please let me know.
No, sir, it's completely fine. You can go with your presentation.
And what about the audience? They're all civil engineers, right?
No, sir. Actually, they are from various different domains. But most of them are from civil engineering itself. Yes.
Okay. So how do I get the pulse of the audience? Is there any way through this StreamYard?
Sir, actually, yes, sir. After your presentation, the audience watching you will be asking doubts and will be forwarding them to you, and you'll have to clear all the doubts in that mode, in this way itself.
Okay. Okay. So it is live, and people are watching from their respective
Y-
places.
Yes, sir. Yes, sir. It is live in YouTube.
Okay. Because I'm just getting myself familiar with the system so that you can speak accordingly. All right. All right. Then I think I'll start speaking. In case if you have any trouble, you are able to see my screen, and I also
Yes,
want to
sir. Yes, sir.
whether you are able to see the next slide. 1 second. You are able to see next slides, right?
Yes, sir. Yes, sir. It is.
Okay. All right. So let me speak. Start making the presentation. Good morning to all of you. I wholeheartedly thank a very interesting club called CIS, right? I think you are civil engineering students technological club. Very interesting.
Excuse me, sir.
Yes, please.
Sir, would you be able to turn on your camera if possible? Or
Yes.
yes, sir.
Let me check how to do that. Is this fine?
Yes, sir. Yes, sir.
All right. You're able to see me now. Okay, good. And should I keep this audio? Sorry, yes, camera always on?
Yes, sir. Actually, if it's possible from your side,
No, no, no. I
you
don't have
should
any
keep.
problem. Okay, thank you.
Okay, sir.
All right. Again, I thank these interesting club members. Very interesting to see that you have a technological club. We usually have a social club, fun club, and of course sports club. But this is very interesting to know that you have formed a very useful club, technological club. I really appreciate that, and I am also thanking the organizers to invite me to talk amongst you today this morning. Okay, so like you all, most of you all at least, I am also a civil engineer. And then because of my master's and PhD, and then later on, even in profession, I myself, specialized in ocean engineering. And I'll probably give you very a brief overview of what we do, not just under my supervision, but also those who are working as part of the ocean engineering discipline at IIT Bombay. Okay, so we'll give you glimpses of what we do in terms of research, in terms of, like you said, even the industrial interactions and so on. Okay, so I'm going to share some of our exciting experiences. So my talk is going to go like this. I will throw light on what we have accomplished in the recent past, maybe a decade plus of time, kind of facilities that we have developed and set up, and the kind of projects, research funded projects that we have successfully accomplished, and also some are actually ongoing even today. And time to time, we also interact a lot with the industry, as you may be knowing. IIT faculty members, based on their expertise and experience, we also give consulting services to the industrial problems. Okay, I will also try to speak a bit about that at the end of this presentation. Like I said before, I'm also a civil engineer, like most of you, but then only my master's and PhD is specialized in ocean engineering from IIT Madras. I had a short stint in the industry too, consulting industry too, before I come to IIT Bombay for about 4+ years of time immediately after my PhD. And this consulting experience is purely related to, I would say, marine and waterfront infrastructure development in the Middle East and countries spreading in the vicinity of Middle East and so on. Okay. So, in terms of our research interests, and this is also equally applicable, in fact, our industrial interaction as well, that we, and I personally spend, 30 to 40% of our time to understand the fundamentals of the dynamics in the open ocean and also in the nearshore environment, either through, physical modeling studies, or it could even be sometimes computer modeling studies and so on. But whereas most of our time and energy being spent in understanding the reality, I mean the prototype scale or maybe the in situ conditions. So we call it as the applied research, you might be knowing, or maybe the applied science in general. So we try to collect data from the field, measurements, and also we use that to improve our modeling skills and efficiency. And at times we also use this, satellite-based information as well. Probably I will try to touch upon these in the subsequent slides through the case studies of our research experiences. We are 4 faculty members at IIT Bombay, and we are still part of the civil engineering department, unlike IIT Kharagpur or IIT Madras, where they have a standalone department called Department of Ocean Engineering. And even if you look at IIT Madras, from where I have graduated, is also full of civil engineers. Our majority of the faculty members at Ocean Engineering department in IIT Madras, they're also kind of civil engineers. Okay, so interestingly, all 4 faculty members working in the ocean engineering specialization at IIT Bombay are all civil engineers, and of course, you may be knowing them through their web portal and so on and so forth. We have done some kind of a course offering from our discipline in the past, and in the recent past, from 2013 onwards, we started offering MTech program. You may be aware by this time, past 10 years, we have been successfully offering this MTech in ocean engineering. I think the civil engineering graduate with appropriate GATE score, they will be able to get into our graduate program at IIT Bombay. Together, all 4 faculty members of our team, we have wide range of research expertise that cuts through all the ocean engineering disciplines, and we also collaborate with academic institutions in India, and also several and multiple universities across the globe. It's quite natural that we speak to each other and we join hands together, and at times we share knowledge through these kind of collaborations and so on. In terms of research institutions, in case if you are not aware, the abbreviations mentioned here, we interact a lot with the National Institute of Oceanography. This is based in Goa, and National Institute of Ocean Technology. And there are many other institutions which work in the atmospheric and ocean science related research projects. So we always join hands with them time to time. And like I said before, we also try to solve the practical problems through our industrial interactions. Sometimes even the public sectors, they reach out to us for any potential solution for some of their problems and so on and so forth. So we work with major ports, harbors, and other maritime state ports and so on. Okay, so if you know about the waterfront and marine front infrastructures like ports and harbors, these are not just only massive in terms of the capex. I'm talking about in terms of the investment that is required as a capital expenditure to set up these massive infrastructure, but they also require a huge amount of investment while they are being maintained and so on and so forth. So there will always be some kind of a challenges that we try to address through our research expertise. Over the years, we have established quite an interesting range of research test facilities. What you are looking at on the screen at the moment is what we call it as wave flume or wave tank. And this tank is basically 50-meter long, 50-meter long, 1 meter by 1 meter cross section. And we have, in this particular photograph, we are not able to see, maybe in the next photograph I may have. We have a computer controlled wave making system being installed in this tank, and that can probably be controlled using some kind of syntax, or what we call it as some kind of a protocol through the computer, and probably it will generate waves in the water tank, exactly what you intend to do, the structure being subjected to, and so on and so forth. Okay, and yeah, there is one another tank that we are right now building, and we are thinking of actually equipping this tank not just only the waves and also with the currents. Actually, if you look at if you ever been to open ocean in your lifetime before, the waves that you see when you go to beach, and the waves that you enjoy by wetting your feet and all that, they are basically wind generated waves. Okay? On top of that, we also have water level which is going to be varying over the time, which is called tides. This is due to gravitational pull of the sun and moon. Okay? And for you to witness the tide, probably you may have to stay there in the beach for about 3 or 4 hours of time. If you just spend only 1 hour, probably you'll not be able to see or realize what I'm trying to tell you in terms of tides and currents. But if you spend 3 hours to 6 hours of time, you will be able to see that the water level of the sea is going to be increasing and decreasing, with respect to the time. And yeah, the waves anyway you will be witnessing when you go to beach. If you happen to visit any beach, probably you'll be able to see. And when you also see the waves which are coming very close to the beach, they will actually have some kind of a breaking event. Probably you now would have really cherished, enjoyed getting wet by this breaking wave and so on and so forth. So all of these are kind of some kind of dynamics that we are trying to understand. There will be certain amount of forces and loads exerted by these waves while they are not breaking and while they're breaking and so on. So all of these are actually kind of interest to us as an engineer working in the ocean engineering field. We do have some interesting range of highly sophisticated laboratory sensors and equipment. You may be aware. These are also be of good use in the civil engineering test facilities as well. Laser Doppler velocimeter, acoustic Doppler velocimeter, and so on. And we do have, apart from the conventional tools, we also have this kind of sophisticated instrument as well. We recently procured, at least interesting to me, this interesting equipment. What we call it as the motion capturing sensor system. It works based on the principles of infrared, and these cameras can be kept little away from the object whose motion you are basically interested in measuring. Let's say, for example, if you have a floating body like a ship, this can undergo all 6 degrees of freedom motion, left floating in the water. If there are waves, and these waves can actually make the ship in all 6 degrees of freedom motion and so on. So if you want to measure the displacements of a particular floating object like a ship in the open ocean, or for example in the testing tank, then you have of course some kind of a conventional way of measuring the displacement, maybe using an accelerometer or maybe using a displacement sensor and so on. But then any of these sensors have to be put inside the floating body itself. Usually the model size will be very small in the tank, testing tank like our physical model facilities. And addition of any weight, sensors, cables, and all that probably may affect the motion behavior of the floating body itself. But the use of infrared cameras like this, you don't need to make any physical contact to the floating body as such. It can actually measure all the 6 degrees of motion without touching the floating body. So that's the advantage. A little sophisticated, and we are thankful to the funding agencies, with who support independent software. We are able to procure this, and we are effectively using this for some of our research studies. Students like you, many students, they have worked with me as summer interns and winter interns. Those who are in the third year, end of their third year, maybe even in the final year stage, they come to me. And they were not only very excited after looking at the kind of research that we do, but they're also ready to take up some challenges. There were some very good examples, especially this particular case study that is being projected on the screen at the moment. He is done by a third year student, a civil engineering student from I don't remember the college name exactly, but he's somewhere from Maharashtra. So he came down, and I told him that we have some kind of a challenging topic to you, whether you will be able to crack this in short period of time, because usually the internship periods are not more than 2 months of time. So he must be doing that. He was ready to take up the challenge, and not only learned by himself, but he also has brought very interesting results at the end of the research project in just 2 months of time. Very excellent time frame he was actually working. So this is actually called Microsoft Kinect. In case if you are familiar with online or video gaming, this is used for the video games. If you want to play cricket in the animated mode on the screen, this is going to be kept behind you, and it captures basically your motion, and then it converts into the equivalent, mimicking equivalent to animation in the computer and so on. But we use this game tool successfully for the first time for our engineering purposes, okay, in the laboratory scale. So I'll speak more about this in case if you are interested. And there are some students who are also kind of came up with customized sensors developed by themselves to measure some parameters in the laboratory scale. And the one that is projected on the screen at the moment is called what do you call the proximity sensors. It is also working on the principles of infrared I did. But then they usually measure the proximity, how close the object is with respect to some kind of equilibrium or something like that, a mean position and so on and so forth. So we used a non-conventional measurement system also successfully in some of the studies. You may be wondering, why is this important? But this is really interesting to youngsters like you, in the sense that they're not only cost effective in the first place, and but they also give you a lot of learning experience, because you have to start from scratch. This is not meant for the purpose, which you are intended to use. So you'll have to probably tweak their usage, and maybe you may have to write a algorithm or codes programs of your own to use the data that it collects in different format, but you are allowed to convert it into the engineering parameter format and so on. So that's what exactly I'm trying to tell you. There are students who have successfully completed experimental research, extensive experimental research, especially the one that is projected on the screen at the moment is done by one of my PhD students in the past. And she had come up with a very novel idea of how we can enhance the wave energy along the Indian coastline, because unlike the northern latitude countries in Atlantics and Pacifics, we are in the tropics, and we don't really have the wave energy that can be really tapped into the electrical power and so on. It is not our fault. It is the natural system. That is how the tropical countries are actually working. So we know that, of course, well ahead of time, and then we wanted to see whether we can enhance the wave energy by some means. So this is one such kind of outcome, and very interestingly, this is already being patented by us, and very, even more excitingly, that the patent certificate was released just last week. Although our efforts were like past more than 5+ years of time and so on and so forth. We don't just only work in the closed environment like inside the campus, in front of the computer, or just inside the laboratory facility, but we also go out, because we strongly believe that the open ocean dynamics are actually a lot to understand. And just by adopting simple model scale and doing some experiments, probably will be able to capture the turbulence characteristics of the open ocean. So we equipped ourselves over the years to be capable of actually doing the in-situ measurements. So this means we go out to the actual ocean by hiring a boat, or hiring maybe sometimes even a bigger ship and so on. We go out, deploy the equipment, and measure the engineering parameters, the actual sea conditions for quite some time, and then we retrieve these equipment back and analyze the data, interpret the data. Using these data can be make forecasting or endcasting, and all of these we do. But then obviously you require a lot of field measured data sets. So we do have wide range of field measurement capable of equipments with us. The right extreme is called recording type current meters. Not just only it measures currents, but it also measures turbidity, salinity, temperature, pressure recordings, and so on. So with one single equipment that you deploy, when I say deploy, we usually go out to the actual ocean, and then we deploy this using some kind of a special frame designed by us, fabricated by us, and we put this equipment, and then we lower it into the seabed. Okay, most of the water depth is usually less than 100 meters of water depth we are talking about. And we do have acoustic current profilers. This means when these profilers are being deployed at the bottom of the seabed, it can continuously measure the velocity of the currents and prevailing currents at all various levels. If you have, for example, deployed this equipment in 100 meters of water depth, it can measure from 100 meter to 0 meter depth, all the current profiles at various levels and so on. So we do have floating buoys which can measure the wave characteristics. I'm talking about the wind generated wave characteristics. And we also have echo sounders. You may be aware of echo sounders. These are meant to measure the seabed contours. like the topographical survey, we also do seabed contours, which actually govern the hydrodynamics in any particular place of our interest. So we do that. I'll probably try to share some of the case studies and so on. And this is actually about us, and I'll probably walk you through selected funded research project that we have successfully accomplished, and few probably would be even still ongoing, and whatever we have successfully brought out as the research outcome, I will be able to speak to you in this presentation. Well, I'm going to take you through a little bit of theoretical part, not more than 5 minutes for sure, so that you don't get really bored of what I'm speaking of. And I'll also try to run through the equations in case if you are afraid of the equations and so on. Well, I'll tell you the dynamics of open ocean, for that matter, in very specifically, even for that matter, entire atmospheric as well as the oceanic process are not just vary in space, but they also vary in time, okay, different scales. Okay, so if you look at the spatial scale, they may be a few centimeter to hundreds of kilometers, and in time they can be few seconds to even days, minutes, hours, days, and so on and so forth. So the it's actually completely up to us. What is the range of time and spatial domain that we are trying to address? One probably cannot uh, try to cover all of this entire spatial and time domain in one single framework of research and so on. So I also have strongly believe in that particular fact. So if you look at that, there are events which are actually happening in very short period of time. Like you would have probably heard about capillary waves. There are small ripples or formations of the undulations when you blow in a bowl of water. If you take a bowl of water and then you try to blow, through on top of the bowl of water, probably you'll be able to create some kind of disturbance at the surface level, right? And we call it as the capillary waves. They will obviously die down after some time. If you stop blowing, they will also be come back to the equilibrium after some time. I hope you know what brings them back to this equilibrium, right? And this is nothing but what we call it as the surface tension, right? The intrinsic principles or the fundamental principles or the properties of the water itself or the liquid itself is going to bring back the disturbance into equilibrium after the force, whatever the blowing force being stopped actually. Whereas once they grow, their causes of the forces which are causing the disturbance, as well as the restoring forces, are going to be different. Okay. So these are small level disturbance we are talking about. When you go to beach, you see the waves are actually of the order of half a meter, 1 meter height, and so on and so forth. And during the monsoon period, or maybe during the cyclone period, of which I really don't advise you to visit the beach, open beach anytime, okay, during the cyclone. But if you get to see in the newspapers, the waves of the order of 2 meter to 5 meters, 6 meters, 7 meters, and there are really high waves and steep waves will be approaching the coastline during these extreme events. Okay. But their periods, the natural period of these waves are going to be of the order of 5 to 15 seconds. Whereas the tide that I was talking about, the gravitational pull of moon and sun, they are actually in hours. Okay, there are some events which are actually going to be repeated in minutes, and there are some events which are going to be repeated in years and so on and so forth. So there are, of course, a classification of which are happening instantaneously, and there are events which I am particularly interested. There are engineering infrastructure which may have adverse effect or maybe even the positive effect over the time and also over the space. For example, if you try to construct a harbor along the coastline, and I'm sure you will all agree with me that the impact of such kind of massive infrastructure being built along the coastline will be felt not just only along the coastline but also over the time as well. I think you agree what I'm trying to tell you now, in space as well as in time. So if you look at the coastline, the west as well as east coast of India at least, the hydrodynamics due to the waves and tides, and now you can also imagine if there are some kind of a river, major river, which also brings in some kind of a discharge, they will also try to influence the hydrodynamics in the nearby area or in the vicinity and so on. So the dynamics also, the dynamics vary basin to basin. For example, the cyclone characteristics in Bay of Bengal is not same as Arabian Sea, or even the wave characteristics in the Arabian Sea is not same as the Bay of Bengal. Or for that matter, these two are different from the Indian Ocean and so on. So the hydrodynamics not only vary basin to basin. When I say basin, Arabian Sea is a basin and Bay of Bengal is a basin. Within the basin also they vary. For example, in in Arabian Sea, along the west coast of India, the hydrodynamics vary a lot from Kerala or maybe the tip of Tamil Nadu, the Tuticorin, to all the way up to the Gujarat, the Gulf of Khambat coastline, and so on and so forth. In every place, I think. So the dynamics is not a generic concept that we can understand through one single approach. It has to be basin specific, and it should also be coastline specific. So, and even if you look at along the west coast, as the same discussion holds true even for the east coast as well. The dynamics are actually different in Tamil Nadu, in Andhra Pradesh, and Orissa, and West Bengal, and so on. So we obviously have to understand these hydrodynamics individually and also specifically to the place which we are interested. Well, I will try to skip this part. The point of presenting this particular slide. Sorry. I hope you're able to see.
Yes, sir.
Okay. So the point of projecting this particular slide is that even the computational tools that we have, although we claim that we have really advanced in terms of the computer models to capture the dynamics in general, let it be aerodynamics or be chemical engineering, expertise required, mechanical engineering, or it could even be fluid dynamics very generally. But all of these dynamics are being now beautifully captured by set of numerical tools that are already available, and it has been kept on improving the efficiency of how well they can actually address these dynamics and so on and so forth. But still, you all would agree with me that there is a term called turbulence, right? And then this turbulence never been understood completely. What we have achieved so far, in my opinion at least, is that we try to approximate as best as possible to the best of our practical use. Okay. And once you have reached to a level of this is sufficient for me, beyond which I don't require any more accuracy, then you stop there. But then still there is a huge amount of approximations involved at this stage of your educational curriculum. I just wanted to say that the turbulence is something that probably we are yet to understand completely. I think all of you would have done an experiment called Reynolds die test as part of your fluid mechanics lab, where we have a vertical tank with a pipe, and then there is a wall, and you also have a red color dye or blue color dye being injected at the middle of the pipe, and the opening of the wall will make a laminar flow to transition flow and then to turbulent flow and so on. I think if you look at the dye streamline or streak lines, the dye will be very uniform during the laminar flow and so on. And then the more the valve opening, then it leads to turbulent regime and so on. You will never be able to recreate the same scenario even in your own laboratory, however be the accurate opening of the valve. Okay, so this is one simple example how the turbulence cannot be really understood properly. Okay, so this slide is also just to make you to realize that there are a lot of unknown parameters even in the mathematical modeling. See, when you say mathematical modeling or computer program, these programs are actually built on top of some kind of fundamental equations. Okay, there will be some set of fundamental equations. I'm talking very generic now. This is nothing to do with just only ocean engineering. This is actually, I would say, probably the entire fluid dynamics I'm talking about. So there are there are fundamental equations for example, your mass conservation equation or continuity equation or momentum equation or energy equation and so on. So on top of which these mathematical models have been built. But then when you solve, there will be a lot of unknowns. Okay, so and these unknowns are most of the time are either assumed, or maybe you may have some kind of a limited understanding of the previous experience and so on. and you use that, based on your wisdom, and then you get the desired results and so on. So in a way, in simple language, we are little bit tweaking actually these unknown parameters to achieve the desired results and so on. I think this is acceptable fact because the turbulence being still largely unknown to every one of us. So what we are trying to do to see whether we can make, instead of making assumptions, can we make assumptions based on some kind of informed decision, something like that. Okay, so that is exactly what we are thinking of actually doing through this airport. And we do have a wide range of resources for that. One could be if you want to fill the gap in the understanding, then obviously you have to go out to the real world outside and then make the measurement of your own and so on. But then in situ measurements or so-called field measurement campaigns are not that easy. You should have not only highly expensive equipment, number one. You also need huge amount of energy and effort. You need manpower, boat hiring, and so on and so forth. In spite of all this energy spent, effort being taken, ultimately you will be able to measure only from one particular place. Okay, wherever you have installed the equipment, only there probably you will get all these engineering parameters. What about the rest of the other places? For example, if you take a coastline in front of the Orissa or coastline in front of Mumbai, it's not just only one point. It's actually spreading into several kilometers. Like I said before, the dynamics are actually varying with respect to space as well. So if you make only one measurement, what is the use of that? In spite of spending so much of money and effort and so on. But the advantage of making in-situ measurements, provided you use the right equipment, that this is the real data of the actual physics that is happening in front of you in the automation. That we know, of course. Of course, it cannot predict more. It cannot actually be invested for long-term measurements. It should usually be in a very short period of time. For example, most of our measurements in our team is not more than 2 weeks of time. We deploy, take it back, and come out. And we cannot actually keep this for a long period of time. I'm not very sure if you're aware that even to mobilize the boat arrangement and manpower and all that, just to make 1 week or 15 days of measurements of the particular data, you still have to shell a fortune out of your pocket. So it's really expensive actually. So computation models exactly fill the gap here. But like I said before, they are built on top of the fundamental equations plus plenty of assumptions. Okay, we have to be very careful. If you give garbage in, they will give garbage out, which we know as a computer program. So we need to give the right input. Only then you'll be able to get the desired results at the end of the day. So quite obviously, the model requires calibration or the validation process. Okay, so which we call it as. But the advantage of using numerical model is that it can go back in time and you can also go ahead of time. It can be used as a predictive models. It can even be used as a hindcasting models time. So you can go, back and forth in time. And that is not possible in in-situ measurement. So you can measure only what is happening just right now. I think we also started using effectively time to time the advantage and the powers of remote sensing. Satellites are there already, plenty of them are hovering around. So we get a lot of engineering parameters as well, provided you write the appropriate algorithm to. They're basically images. Satellite basically gives us images, but then the images are not just photographs. They have huge amount of engineering parameter inbuilt in them. Again, provided you write the appropriate algorithm to extract this information out of it. We have done it successfully. The advantage of using such kind of a satellite imageries is that they cover, being in the sky, they were able to cover large spatial domain. Okay, one single snapshot probably you can cover nearly 1/4 of the entire Indian subcontinent as well, if really required. And but since they are still requiring some kind of algorithm to extract the engineering parameters, we need to have some kind of a ground truth data from the actual field measurements. It can be limited as well. Then use this for actually to make sure that your predictive algorithms are actually working well and so on and so forth. On top of that, you also use sometimes the models like analytical models, probabilistic models. If we have a lot of data and you really have a lot of randomness, then you use some kind of a probabilistic data, and we also do physical modeling test in the laboratory and so on and so forth. The reason why I try to project this particular slide to you is that we have different resources like the in-situ measurement capabilities, mathematical modeling, you have computer resources, you also have plenty of satellites being hovering around us. But then how to judicially mix up all these powers of these individual resources to achieve the common goal of your research objective and so on. So that's exactly what I'm trying to project in this particular slide. Of course, we have done a lot of research project as well as industrial project using all of these powers. Probably I'll highlight a few of them in this particular presentation. This is actually done exclusively for Maharashtra government by our team. I'm not very sure if you guys are aware of two infamous incidents along the Mumbai coastline, two ship collisions, sorry, two ship accidents. One is kind of sunk during the monsoon period, and the other one was kind of a head-on collision between two ships and so on and so forth. I think this was 2010 and 11 time, I guess, in front of Mumbai coastline. So when the ship accidents happen, most of the time there will be some kind of oil leaks coming out of these vessels, and they spread in the open ocean waters. And the oil being actually, floating in the surface like a sleek, they can easily be driven by the wind and also the currents. And sometimes they also reach along the coastline and may sometimes create some kind of a huge environmental and ecological crisis, okay, along the coastline. This has actually happened in the past in many places, not just only in India. And this particular project was given to us to understand, in case if there are any accidents in the ship accidents in the open ocean and of Mumbai coastline, can we predict where the oil leak will end up along the coastline, whether north of the coastline or south of the coastline, or where it is going to be land up in Mumbai city, so that the disaster mitigation team can be mobilized quickly. Then probably we can minimize the damage in time. So that's the idea. And we used again powers of the remote sensing. We were lucky to have some incidents being captured by some of the satellites passing over the sky during that period of time. And what you see basically, I'm not very sure whether you are able to see the mouse. The left upper photograph picture is satellite image being processed. For you to see the red patches are nothing but the oil leaks. Okay, so this is being taken from the sky, I mean satellite imagery, and using our own in-house algorithm, we were able to clearly see the leaks, oil leaks in the open ocean water. And Mumbai is being shown here. I'm not sure whether the mouse can be shown. Okay, fine. And we also used mathematical modeling, and we developed a small graphical user interface which can give any user or any stakeholding agencies, for example, Coast Guard, or it could be disaster mitigation department, or it could be coastal police and marine, departments like maritime boards, oil companies, and so on. So they can plug in, where the ship accident happened and what amount of oil being likely to be released. Then within the next few hours, we'll be able to get how the dispersion of this oil leak is going to appear in the next 1 week to 10 days of time. Okay, so you can actually be prepared by the time. And some of our students have actually spent a huge amount of time in understanding how the sedimentation happens. I think you would probably have heard about terms like ports and harbors and associated components, key components of the ports. One of the important component is called navigation channel. Okay, so every single commercial ship requires certain amount of water depth, and these water depths are usually not available all the time very close to the coastline, but the ship has to come to the coast, very close to the port as well. So we usually dug channels which cannot be seen from the water, only it is marked with marker points, and those pilots who are actually navigating the vessels would be knowing where the channel is actually existing. For the common man, it is very difficult for us to make. But these navigation channels are actually nothing but artificially dug channels inside, below the open ocean I'm talking about, and inside the seabed, and through which the ship can safely come without getting grounded to the ports in and out. Okay, but these channels being artificially dug, and they have a tendency to get silted up because the currents are always prevailing due to the tides and waves, and sometimes even due to the river discharges and so on. So these channels are frequently getting silted up. Okay, and you need to maintain certain amount of water depth all the time in the channel so that the vessel can safely navigate without getting grounded. Okay. But what authorities usually do, they do some maintenance dredging. Dredging means removal of this silted material in the navigation channel for the safe passage of the vessels. They spend a huge amount of their revenue towards keeping this channel navigable. Okay, so they do dredging every year. They remove the siltation and all that. So this particular study was just to understand how much is going to be silted up. See, minimizing the siltation is one side. We are talking about the mitigation measures. But even for us to be prepared financially or in terms of ahead of the planning of the next year budget and so on, we need to know how much is going to be silted up every year, right? And this is exactly what one of our master students have done successfully. So he combined, he of course taken a lot of field data. He also has brought some of the data to the laboratory to further analyze it, and then he put it actually in the computer models, and then he do kind of a parametric study to arrive at the quantum of material going to be silted up next 6 months, next 1 year, and next 2 years, and so on and so forth. So this was also a very interesting and exciting research project done by one of our students. I think being in the ocean engineering field of research, we also spend quite an amount of time to understand how the marine renewable energy resources are actually spread in space all along the Indian coastline. So when we talk about marine renewables, we are talking about wave energy, tidal energy, or it could even be offshore wind energy and so on. So something similar to your, the on land wind turbines. Ministry of New and Renewable Energy is also thinking of actually deploying turbines in the open ocean. The advantage of actually having offshore wind energy is that you get winds continuously, uninterrupted. Unlike the land-based wind energy, which at times affected by the seasons, like in some season you'll have less wind energy, obviously less electricity production. Offshore winds are actually more or less they're very constant throughout the year, and it is actually highly feasible technically and also commercially viable and proven many places in the globe. So what we do at this stage is that we are trying to map the energy resources available in India, okay, in various forms. We have some students working on the wave energy, some students working on the tidal energy, and so on and so forth. So we are trying to map, and we also time to time collaborate with our international partners to see whether we can exchange our experiences, maybe the challenges being addressed by each other, and so on. I think this is part and parcel of every single academic institutions like ours, IIT Bombay. We also do a very frequent knowledge sharing exercise like this, knowledge dissemination activities, and at times we also do outreach activities. We help mobilizing students, staff, scientists to travel to other places and have some kind of brainstorming sessions, workshops. We conduct technical seminars, and we have organized even conferences at national level, or maybe some kind of a interinstitutional collaborations and so on. Many of them actually we have done successfully over the years. All this is our commitment towards the knowledge sharing to a larger community. We have done some successful field measurement exercises in collaboration with other institutions. I think this particular exercise was actually spearheaded by IIT Bombay. We have brought multiple institutions across the country, and we were also kind enough to have our counterpart collaborative institutions from Taiwan that we launched actually a field measurement campaign, but spearheaded by IIT Bombay. This means we coined this idea, we conceived this idea, we charted out the plan, and we brought all the people in one particular place, and we deployed our respective equipments. Each one of them they have brought their own set of equipment. We deployed it in the open ocean. and we collected the data and shared it across the institutions, and then each one will obviously look at the data, same data in different perspectives. So that's the whole idea of doing this exercise, and it's also being positively commented by our Ministry of Earth Sciences and so on. I think this is something to understand how the artificial beach being created in one of the southern states in Tamil Nadu. It's a place where the beach was quite famous in the past, but then it got completely eroded and disappeared over the years due to the various infrastructure development reasons. But then the government wanted to restore the beach by artificially creating the beach, and the beach may not stay unless being supported with some kind of engineering infrastructure. So this study was to understand how the engineering infrastructure influence is going to be changing the local dynamics, nearshore dynamics. So we deployed uh, equipments in different seasons, and even during the construction of the infrastructure as well, we try to map through mathematical modeling and so on. So this is an exciting experiment. We have done it very successfully. And if you look at the bottom right corner, also the left pan, and I actually compared two different data sets. One is actual field measurement data set, and the other one is mathematical mimicking of the same, or computer modeling of the same. Okay, for example, the right down corner, the Google map is actually being overlaid with the drifters that we have done as a field experiment. We use the GPS fitted drifters. We throw open in the open water, and then the drifters are actually naturally driven by the currents of the prevailing currents in the nearshore environment. And then we continuously map not only the velocity but also the trajectory. And the same can also be mimicked in the mathematical modeling, computer modeling as well. And what you see with thick brown color in the mathematical modeling is the engineering infrastructure that is being under construction during that point of time. So we wanted to know the influence of the engineering structures, although they're very small structures, the engineering structure being influencing the local hydrodynamics greatly in that particular way. And same is the case with the left pan picture, where we have the measured values as well as the computer model values. I think this is a kind of a repeat of what we have done it in the artificial beach nourishment project that I had discussed about in the previous slide. This is actually natural beach somewhere south of Maharashtra coastline, and we try to understand how the sediment dynamics actually happen. So we specially designed some kind of a sediment streamer. Our engineering team was equipped and trained to measure and also to use this equipment very specific purposes and so on. We also bring some samples to the lab, analyze, and then use this information in the mathematical modeling and so on. I will skip these slides. It may not be so interesting to you. And when it comes to the mathematical modeling, we always have a simple approach called global to local model, because the waves are actually not coming from just nearshore environment. If I say when I go to beach in Mumbai, the waves that I'm going to see is actually not coming from Mumbai. They'll be coming from elsewhere, maybe in the middle of the ocean and so on. So it is always our principle to see global to local. You'll have to understand the dynamics from large scale and the entire basin scale to local regional scale and then to local scale and so on and so forth. So we do that, of course, very systematically. And this may be at this stage slightly more for you to understand, but it's okay, I think. We also started using effectively the low-cost drones to understand. Apart from the satellite imageries, you can also fly the drones, although they can fly only for a short period of time. But still, you can make a lot of engineering parameters. This particular slide that I'm showing here, we've taken some 5 minutes of videograph of the waves in the nearshore environment. The drone was actually flying about 400 meters above the ground level, and it was actually hovering in one particular location. And once we get this video, we have some kind of automatic algorithm developed by one of our students to understand the wave characteristics, how rapidly they are changing when they approach the coastline and so on. Okay, so this is very interesting project that we have successfully accomplished. Whenever we go out to the field, we always learn a thing or two. When we come back, I think every single fuel measurement campaign has taught us something different. I think this is something that we have done it for Ministry of Shipping, for a port. It's called Kandla Port in the Gulf of Kutch in Gujarat. This is also related to the navigation channel being silting up. We have spent 2 years of time to understand. But in this particular study, we have also gone ahead just after the field measurement mathematical modeling. We also gone ahead to suggest some kind of engineering solution to minimize the expenditures towards the dredging activity and so on and so forth. We have demonstrated the use of low-cost drone again to capture the topographic features. For example, the photograph shown on the left corner is a marshy land where the conventional survey equipment like your total station or it could be dumpy level, all of this equipment cannot be used because this is a marshy land. The moment you try to keep the equipment, it will actually go completely sinking at least for about 2 to 3 feet inside the marshy land. So you cannot walk inside these marshy lands, but you cannot use any conventional survey equipment to capture the topography. And we demonstrated using these local drones, we were able to map the entire topography in very short period of time. For example, the one that is being projected on the screen, the middle picture, the orthomosaic image, is covering about 6 to or maybe 5 to 6 square kilometer of area, and the entire topography was captured unbelievably in less than half an hour of time, or maybe half day of time together. All our ground control point, everything together. If you use the conventional survey equipment, probably it will take ages to make the topographic map. We have done it very successfully. I think I'll skip this. We effectively use the remote sensing imageries in many of our research projects. I'm sorry to run through. I thought I'll actually skip some of the slides so that we will have time for discussions and so on. This is another interesting research work done by one of our PhD students. We're all aware that the reinforced concrete being exposed in marine environment, being the saline water, the reinforcement inside the concrete is going to get corroded over the time, and they will deplete in no time. Okay, so the reinforced concrete, once after 15, 20 years of time, I think they'll start initiating the corrosion inside, and then the reinforcement bar is going to lose its circumferential area or the cross-sectional area, and the desired amount of strength or load carrying capacity of the structure is going to be slowly coming down. And our student has actually spent quite an amount of time to understand this corrosion behavior first, and then to give some kind of mitigative measures as well at the second part. Very interestingly, we got 2 Indian patents for this particular work, and thanks to many of the Indian government and intergovernmental agencies for funding us, and without which all the slides that I have presented in the past weren't really possible actually. I personally work with the industry. I have experience working with in industrial projects in many different countries, and most of our interactions are actually with respect to marine infrastructure or waterfront infrastructure projects related to ports, harbors, artificial islands, or it could be even marinas, waterfront developments, and so on. And so we have worked actually a lot, and we do have design capabilities to take care of all the marine infrastructure projects and so on. Currently, we are also working in the conditional assessment. I think, as you know, the civil engineering infrastructure is going to get age-old or age-related issues over the years. I think marine structures are usually reaching this stage very fast. So we work with the port industries to understand how bad the conditions of the existing infrastructure, and of course, when we have to make some decisions whether to demolish or to repair, we need strong engineering, information supported decision. So we do field tests, we do lab tests, we do modeling, and then we come to a conclusion to continue with the structure or to be replaced with a structure, new structure, and so on and so forth. I think with that I will try to stop. We also have some interesting range of ongoing industrial projects as well. Thank you so much for the time, and I'll be happy to answer any questions if you have.
Sir, there are some questions.
Yes, please.
So, what skills are highly valued in ocean engineering?
What skills mean? What exactly is the question? Actually, I didn't get the question exactly. You mean computational skills, or what do you think? What do you want to know? Yeah, I'll say that, see, ocean engineering is, in my opinion, of course, I'm being a civil engineer, it encompasses all the engineering disciplines of civil engineering. Okay, so we have people with a geotechnical background, we have structural background, we have water resources background. So all of this is also required a bit to manage infrastructure project in the marine environment. Okay, and at times mechanical engineering also is also required in the offshore industry and so on. So I'm not very sure what was the question about skills here.
So, with the growing interest in deep sea exploration, how can ocean engineering prevent catastrophic event like ocean gate Titan somewhere and implosion?
Well, unless the complete story of this implosion is known to me, I may not be able to make any comment on that.
Okay, sir. Sir, given the susceptibility of coastal areas, natural disasters, how is ocean engineering involved in designing structures and systems that can withstand events such as cyclone and tsunamis?
Well, to answer this question, I think uh, if you look at the global human population, even centuries together, my dear friend Akash, we always try to live along the coastline. I'm not talking about just now, I'm talking about centuries ago. Human settlements are always depending on the resources, either along the banks of the river or along the coastline. And even today, I think 18 out of 20 top global thickly populated cities are actually coastal cities. Okay, so we depend on these resources one way or other. For because of the tourism, we like these oceanfront, coastal front, because of the transportation, like the harbors, ports, which can actually mobilize the large amount of cargo in single shot. And in terms of resources, like you have oil, gas, minerals in the open ocean. And in terms of you can say fisheries, food resources, and we always try to live along the coastline. Okay, for example, even Bombay is a thickly populated coastal city, Chennai, Calcutta, and so on. Quite obviously, you are also exposed to hazards like the natural disasters. Okay, when you try to live along the coastline, you will have to be prepared for these hazards as well. So we engineers constantly think, improve our design strategies, and we try to forecast these events. And when we design that, we always keep long term in our mind. Okay, most of our marine infrastructure is actually designed for at least 25 years of return lifespan actually, or maybe 50, 100. So that means we always go ahead in time and then forecast what would happen in next 50 years, 20 years, 100 years of time, and our design strategies are always being changed accordingly. So we do really take care of those when we design these infrastructures.
Okay, sir. So, how can ocean engineering contribute to the sustainable development of marine resources in Indian subcontinent?
This is a big subject of its own, sustainability. I will speak from an engineering perspective. Right now we are working on alternative material compared to the reinforced concrete in the marine environment, because we know that the steel placed inside the reinforcement concrete is going to get corroded, and we are actually thinking of working in some kind of sustainable material in the long run. This is from the engineering perspective. Or in case in terms of the resources perspective, I think there is a huge number of effort, it's a huge amount of effort and huge number of schemes being announced by multiple industries, multiple ministries by the government of India, including Ministry of Earth Sciences.
Thank you, sir. So we have approached the end of the session, and I would like to invite Secretary of the Chess Club for a vote of thanks.
Can I stop sharing?
Yes, sir.
I hope I stopped
Good
sharing.
afternoon, everyone. Good afternoon, everyone. I am Mehak Fatima, the secretary of the CEST Club, here to express our heartfelt gratitude. Firstly, I extend sincere gratitude to Professor Ramakrishnan Balaji for gracing us with his presence and sharing his profound knowledge on ocean engineering in this session. Sir, your expertise has added to the immense knowledge, and we are truly honored to have had you as our guest speaker. To the audience, your active participation and enthusiasm has made this event truly special. We hope you found this lecture as enlightening and inspiring as we did. Again, a heartfelt thank you to Professor Ramakrishnan for his valuable contribution and our wonderful audience for making this seminar session a success. Thank you for joining us.
Thank you so much, sir, for coming to this session and enlightening us with your knowledge in ocean engineering.
Thank you for your patience. I think it's a wonderful arrangement. I really enjoyed the way it is being totally arranged. There was a continuous follow-up from one of your team members about my schedule and about the title of the presentation, and also at this SteamYard, I have very wonderful experience of projecting the experiences. Thank you so much.
Thank you so much, sir.
Yes.
Thank you so much, sir.
Bye. Take care. All the best for your studies. Can I sign out now?
Yes, sir.
Yes, sir. Yes, sir.